Hi, welcome to Thermochemistry 2, Part 3. Today we're going to be talking about free energy. In the AP curriculum, specifically, we're going to be looking at Essential Knowledge 5.E.2 and Essential Knowledge 5.E.3. It is worth your while to read over these and understand them in the context of the notes. Specifically, what we're going to look at today is Gibbs Free Energy, general trends with free energy and spontaneity, standard free energy change, and calculating free energy change. Free energy, represented by the symbol G, is also called Gibbs Free Energy. Free energy is the portion of the energy change of a spontaneous reaction that is free to do useful work. The remainder of the energy enters the environment as heat. Calculating free energy change under constant temperature and pressure. The formula that we're going to use is delta G is equal to delta H minus T delta S, where H is enthalpy, T will be Kelvin temperature, and of course S will be entropy. This equation examines the use of change in heat and change in entropy to predict whether a given reaction occurring at constant temperature and pressure will be spontaneous. General trends. If temperature and pressure are constant, the relationship between the sign of delta G and the spontaneity of a reaction is as follows. If delta G is negative, the reaction is spontaneous in the forward direction. If delta G is 0 for some reason, the reaction is at equilibrium. If delta G is positive, the reaction in the forward direction is non-spontaneous, but the reverse reaction is spontaneous, something to keep in mind. Let's look at an example. For a certain chemical reaction, our change in enthalpy is negative 19.5 kilojoules, and our change in entropy is positive 42.7 joules. Is the reaction exothermic or endothermic? All we need to do is look at our delta H. We see that it is negative. Therefore, this is an exothermic reaction. Does this reaction lead to an increase or decrease in the disorder of the system? Now, we know that if our delta S is positive, that is going to lead to an increase in the disorder in the system. Calculate delta G at standard state for the reaction at 298 K. The first thing that we need to do here is to remember that our delta G is going to be recorded in kilojoules. Therefore, we need to take our value for delta S right here and convert it into kilojoules. That always will be step 1. So 42.7 joules, multiplication sign and a line. We know that there is 1,000 joules in 1 kilojoule. Therefore, when we work this out and we convert it over, we're going to have 0.0427 kilojoules. Now we are in business. So we know the formula delta G is equal to delta H minus T delta S. And then we're going to plug in our values that are given to us. So for delta H, we have negative 19.5 kilojoules minus our temperature, which is 298 Kelvin, times our change in S, which we just found in kilojoules, which will be 0.0427 kilojoules. And if we work this out for delta G, we find that it is negative 32.2 kilojoules. And based off of these results, we can see that we have a negative sign right here. So that answers our question, is the reaction spontaneous at 298 Kelvin under standard conditions? And the answer is yes. Yes, it is, because our resulting delta G at standard state, so put our little standard sign in there, is a negative sign, and that indicates a spontaneous reaction. Let's look at another example. For a certain chemical reaction, our delta H under standard conditions is negative 35.4 kilojoules, and this time our delta S at standard state is negative 85.5 joules. Is the reaction exothermic or endothermic? We look at our delta H, we see the negative sign. That is exothermic. Now, does this reaction lead to an increase or decrease in the disorder of the system? So we look at our delta S, and in this case, our delta S is negative. A negative delta S means that we are going to have a decrease in the disorder of the system. In other words, things are becoming more organized. Let's see how that plays out when we calculate our delta G at standard state for the reaction at 298 K. Again, the first thing that we need to do is convert our negative 85.5 joules into kilojoules, because we know that delta G is recorded in kilojoules, so 1,000 joules is equal to 1 kilojoule, and joules cancel joules, so our resulting answer here will be negative 0.0855 kilojoules. And then we're going to use our formula. Delta G is equal to delta H minus T delta S, and we're going to plug our values in. Our delta H is negative 35.4 kilojoules, and then we're going to do minus, our temperature is 298 K, and our delta S is negative 0.0855 kilojoules. Lots of negatives going on here, so we have to be very careful how these distribute and how our answer plays out. So we know a negative times a negative is going to give us a positive, but our initial number is negative, so when you work this out, you should have calculated negative 9.92 kilojoules, which again, our delta G is negative. So is this reaction spontaneous at 298 K under standard conditions? The answer again is yes, but just barely, because it's negative 9.92 kilojoules. If our resulting delta G was positive, it would be non-spontaneous, but in this case, again, it is negative, so it is spontaneous. Free energy and spontaneity. A summary. Reactions proceed in the direction that lowers their free energy. In other words, we're looking for a negative change in free energy. One way of viewing this is looking at your value of your delta H, your T delta S, your value of G, and then determining whether it is spontaneous or not. So if your value of delta H is negative and your value of T delta S is positive, ultimately your value of delta G is going to be negative and the reaction will be spontaneous. If your delta H is positive, but your value of your T delta S is negative, the value of your delta G, because we're going to have a negative minus a negative this amount, will be positive, and therefore the reaction will be non-spontaneous. Things become a little bit more dicey in this situation, where you have a negative delta H, a negative T delta S. Your value of your delta G is going to be spontaneous if the absolute value of the delta H is greater than the absolute value of your T delta S. In other words, under low temperature. But if your delta H is positive and your T delta S is positive, again, your value of your delta G is going to be temperature dependent. It will be spontaneous if the absolute value of your T delta S is greater than the absolute value of your delta H. In other words, we're looking for high temperatures. So sometimes calculating your delta G can be pretty straightforward, as you see in the top two, and sometimes it's just going to be a little bit more complex. So be careful when you're using this formula. Free energy in chemical reactions. Standard free energy change. Delta G naught is the change in the free energy that will occur if the reactants in their standard states are converted to the products in their standard states. Delta G naught cannot be measured directly. The more negative the value for the delta G naught, the farther to the right the reaction will proceed in order to achieve equilibrium. Equilibrium is the lowest possible free energy position for a reaction, and that is something to definitely keep in mind. Calculating free energy change. Method 1. For reactions at constant temperature, you can use the formula that is found on your reference table. Delta G naught is equal to delta H naught minus T delta S, and that is if you are at constant temperature. Method 2 is an adaptation of Hess's law. So here I have heat of formation reactions that I manipulate around using the delta G values that are assigned to them, probably off of a reference table found at the back of your book. I take the difference of the two and I find it to be -3 kilojoules. So this way of doing it is very similar to what we've done before when we've looked at Hess's law problems. Method 3, using standard free energy of formation. Standard free energy of formation is the change in free energy that accompanies the formation of 1 mole of that substance from its constituent elements with all reactants and products in their standard states. Delta G of formation of an element in its standard state is 0. That's very similar to what we saw of our delta H values. So to find our change in free energy, we're going to take the free energy of the products minus the free energy of the reactants. Let's look at an example. Consider the reaction 2SO2 plus O2 yields 2SO3. Carried out at 25 degrees Celsius in 1 atmosphere, calculate delta H at standard state, delta S at standard state, and delta G at standard state using the following data. So the first thing that I'm going to do is calculate delta H at standard state. And I'm going to do this by taking products minus reactants. So the first thing that I've done here to calculate delta H at standard state is written out my products, 2 moles of my SO3 minus my reactants, 2 moles of SO2 plus 1 mole of my O2. Now what I'm going to do is I'm going to look at the information right here and substitute in my values. So for SO3, I substituted in -396, which I find right here. For SO2, I substituted in -297, which I have right here. For standard state elements, remember that is going to be 0. Now I'm going to do all my calculations and find my overall delta H at standard state. And when I do that, I find it to be -198 kilojoules per mole. So you should be doing this yourself, doing the calculations and making sure that you're checking your work. Let's do the exact same thing now to find delta S at standard state. So again, I wrote out my product and I wrote out my 2 reactant in symbolic forms. I know I'm going to be substituting in these values right over here, and I have to be careful this time because when I substitute in my value for oxygen, that does have a value associated with it. So now I'm going to take this data and plug it in. So I plugged my values in. SO3 is 257, SO2 is 248, and O2 is 205. Then I did my calculations and I found that 2 times 257 is 514, 2 times 248 is 496, and 1 times 205 is 205. Therefore, my final answer for my delta S at standard state is -187 joules per Kelvin. And I know that since I'm going to find delta G here, I need to convert it into kilojoules per mole. So that's -0.187 kilojoules per mole. The last thing that I need to do here is calculate my delta G at standard state. And to do that, I'm going to use delta H, which I've already figured out, minus T delta S. So I'm going to take these values that I have right here and plug them into my formula. So when I plug them in, I have -198 minus 298 times -0.187. When I work this all out, I find my answer to be -142 kilojoules. And remember that negative sign tells me that I have a spontaneous reaction. This is a very common type of problem that you're going to see on homeworks and practice problems, potentially on a test. So it's good to understand how to go through this problem and understand where you're getting these answers. Let's look at one more example showing a different type of format. Methanol is a high-octane fuel used in high-performance racing engines. Calculate delta G under standard conditions for the following reaction. 2CH3OH plus 3O2 yields 2CO2 plus 4H2O. Given the following free energies of formation, and then we have our substances that are involved in the reaction and the associated delta G values. So the way that we're going to set this up is, again, we're going to do products minus reactants. So the first thing that I'm going to do is take the time to write out my formulas. So 2 moles of CO2, 4 moles of water, minus 2 moles of methanol, plus 3 moles of oxygen. Now I will take the data that is given to me and plug them in for my formulas. Writing out the formulas ahead of time is key to avoid making mistakes. Trust me on this. So here I plugged in negative 394 for my CO2, negative 229 for my water as water vapor, negative 136 for my methanol, and 0 for my O2 because remember, it's in its elemental state. Now I'll continue my calculations. So I find that 2 times negative 394 is negative 788. 4 times negative 229 is negative 916. 2 times negative 163 is negative 326. Finally, I'll work out my answer. So my answer is negative 1,378 kilojoules per mole, which means again that this is going to be a spontaneous reaction. And that summarizes a number of different ways of how to find free energy under standard conditions.